Well, it looks something like a cross between a rat's nest and a Christmas tree, but it's my 6502 CPU prototype version, and it's doing fetch, decode and execute. So over here we have the central control board, which is doing all the controlling for the rest of the circuit. Down the left hand side here we've got my programmable ROM, my manually programmable ROM, which is only a temporary thing, so I can write programs in this 16-byte ROM really easily. We have the program counter at the back here, and I've put that onto one of these little decimal displays that I've made. It's not actually part of the circuit, it's just something that I've put on for debugging purposes. At the front here we've got some registers. So this is the A register, this is the X register, this is the Y register. It's got a few other bits and pieces on there that I'm not using. And at the back here I've got another register which is something like an S register, so the stack pointer register. So what I'm going to do is write a really simple program in the memory down here. I'm going to take away the fast clock that I've got going in at the moment. Well, I laughingly say fast clock, it's probably about 10 Hertz or something, and replace it with a manual clock, and I'm going to step through a program just to check that everything's working. What I've managed to do so far is implement a few basic instructions from the 6502 list of opcodes. I think there's about 150 opcodes on the 6502. I've implemented probably about half a dozen, so I've got no operation, which does nothing. Well, I tell you what, let's look at some. Okay, I've zeroed everything out in this memory down here, so all of my 16 bytes of program memory are set to 0. So let's just take a look, make sure we can see that. And you can see that with all the bytes set to 0, the program counter's counting up from 0 to 15. Then it just rolls around when it gets to the end and goes back to 0 again, because it's only a 4-bit program counter at the moment that I've got right at the back here in a 74 HC163. Okay, so now I've gone over to manual clock, which involves pressing this clock button here to step through, and where we are at the moment is at memory location 14, so that's right down the end here. It's going to read each byte in, so it'll be reading from memory location 14 into the instruction register, so they're all set to 0. I've used NOP, I've used 0 as NOP. Actually, in 6502 assembly language proper, it's not 0 for NOP, but I've set 0 because it's easy to remember while I'm testing. So we're going to pull in a 0 and put it in the instruction register, which is here. It's going to be displayed in binary here. Well, it's already got a 0 in it. And then these lights at the back here, which you can not really see, these 4 lights here, they tell you where we are in the microcode instruction counter. So we're currently on, what's that, 2, we're on stage 2. I've set a NOP instruction to be 3 cycles long, so when we pull in a 0, we pull a 0 into the instruction register and we go microcode instruction stage 0, 1 and 2. Then we move on to the next one, 0, 1 and 2. I just happen to have made NOP to be 3 cycles long. It doesn't really make sense to do that, but I just thought it'd be a bit more interesting to see that. Then we see the results of the A decoding here and the C ROM decoding here, and I've just set NOPs to do a 255, which means do absolutely nothing in the decoding. So we move through three clock cycles for each operation when we're doing NOPs. 3 lights on the end here means we're about to end the current instruction. 1 light right over the end here, behind the jumble of wires, that bit right at the far end there tells us that we want to increase the program counter. So when that's high, we increase the program counter. It just went up to 6. When it's low, we don't increase the program counter. So a NOP involves fetching a byte from memory, a 0, doing absolutely nothing, and then ending the instruction. So if I can find a little tool like this screwdriver, I'll put an instruction in the first memory location, so we'll put a 1 in there, and I've set that to be load accumulator with an immediate value, so LDA hash n, whatever n is. And where is the immediate value going to come from? Well, it comes from the immediately following byte, so I'm going to load 129. So we'll do an instruction that will fetch LDA, which is the first one, and then it will go on to pull 129 into the A register, which is sitting right down here. So that's a 2-cycle instruction. Oh, look, we're in the wrong place in the memory. We're right down the end, so we'll wrap round to instruction 0. So instruction 0, when we finish, we're just about to finish that one, we've gone on to the next one. So we've pulled a 1 into the instruction register, that's just here, which is a little bit hard to see. We pulled a 1 into the instruction register, so we decoded that into some instructions to increase the program counter. So we increased the program counter to 1. We published the value of that location onto the bus, passed it into register A, and we're about to end the instruction and increase the program counter again, because we used the command in byte 0, we used the value, the immediate value in byte 1, and we're about to move up to 2. So let's put an instruction there quick before we get to it. Instruction 2 is TAX, transfer the accumulator to X. So if we grab that one, so now we'll move on to memory location 2. We're going to grab the value of 2, and we're going to decode that. Well, we're going to increase the program counter first to 3, and we're going to get the decoded instructions. The left 4 are what we need to publish, the right 4 are what we need to store. So we're publishing whatever is in my location 2. 2 is the accumulator, and we're storing it in 3, which happens to be the X register. So we've transferred from the accumulator to the X register. So if we now want to transfer from, well, let's on the next byte. So that's a single byte instruction, just a 2. Let's try, now let's pull a different value in. So we'll say load A again. We'll load A this time with 15. So you can write the program as you're working your way through the memory. So we will move on to bytes 0, 1, 2, 3. So we're going to pull a 1. So we've fetched instruction 1 into the instruction register, and we're now going to do a load A with 15. So A gets the value of 15 down here. And once we've loaded A with 15, let's do a TAY, a transfer A into Y. So that's a 3 in my made up set of opcodes. So we'll pull in the instruction 3, which will transfer A into Y, which is right here. There we go. So we're doing fetch, decode and execute, and it all seems to be going quite nicely. Okay, so now we come around to instruction 6, well, byte 6, and I'm going to put an instruction 6 in it. And instruction 6 is transfer A to S, so we just loaded up 15 into A. We're going to transfer it into this S register right at the back here, which you can hardly see. So transfer A to S. We pulled the 6 in, and we're going to transfer A to S. There it is. I should do the clock a little bit slower so you can see that in action on the next one. And then on instruction 7, we can decrease S, so that's 8. So the S register is the only one that I've managed to build so far that's got an increase and a decrease ability. So let's decrease it 3 times. We'll do decrease, decrease, decrease. So when I press the clock down, well, you can see this LED's clock active. Well, it's clock high and clock low basically. So I press the clock button and we're clock high. We've fetched 6. We're on 15 in the S register back here. So there's the S register, and as we go through these instructions, we should see it decrease. There you go, it's decreased by 1. So how many times did I say decrease? 3 times, twice, 3 times. So we've decreased it 3 times. And I've got a couple more instructions up my sleeve I can transfer back in the other way. So I can transfer that number back into A. That's a TS, well, there is no such instruction actually as TSA. Transfer S to A in 6502, but I've just made it up because this is sort of a general purpose CPU at this point, and it can do whatever it wants. So we should be able to transfer that value there, which is 12, back into A. Yeah, we transferred that back into A, and then we can, so we're on 11 now, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 will pull, well, let's transfer A into X again, just to get a value to go into X. Transfer A into Y again with the TAY, which is 3. We've got 3 bytes left. We could pull another value into A. Let's pull in 255 because that gets lots of lights on. In fact, let's do a pattern. So we'll do on, off, on, off, on, off, on, off. It's about 170. We'll put that into A, and we'll also put that into Y with the TAY, which is 3. So we should pull that value of 170 in. It's not very clear there yet. There it is. And then transfer it over into Y. So there you go. So now, if I clock, and because of the way the program counter works, we're back to 0 now. So we should be able to step our way around the program, carrying out each of those instructions in turn.